this team as well. We're going to talk about the radio system we developed for this year's IREC and sort of the iteration of that. Okay, so we're going to first talk about RF requirements, sort of just what we need to make a rocket telemetry system functional, what kind of RF we need sort of to make that work. So IREC, sort of, we're flying the 30,000 feet COTS. This is our rocket. So you need a range of about 10 kilometers. In terms of power requirements, you're looking at, because you're going to be on the pad for a long time, you want to have not too much power. So we said around 750 milliwatts would be a good target there. And then you need a certain amount of data in order to send any useful telemetry to or from your rocket. So around 5,000 bits per second is a useful number for that. These are sort of estimates, but they generally do a good job. If you're looking to transmit video to and from your rocket, or well, from your rocket most likely, you need more along the lines of 100,000 bits per second, so significantly more data for that. So those are the sort of requirements for this type of rocket and what we would need. So we also do some other projects at Stanford Space Initiative, specifically Space Shot, which is sort of you launch a balloon to 18 kilometers, and then you launch a rocket from the balloon to 100 kilometers and break the von Karman line, is sort of the goal there. For that, because you're going to 100 kilometers, you need 100 kilometers of range, obviously, and the other requirements are about the same. You're just looking at similar 750 milliwatts and 5,000 bits per second. It's about the same because it's just a rocket. So in the past, we competed last year, sort of most of the teams here are using commercial RF solutions. So this is an XB 900 megahertz radio, standard off-the-shelf component. They're about $70. They work pretty well, they transmit data, they do the job for most teams. So this is a sort of close-up last year. It's just in that little, behind there's a little antenna, a small dipole antenna. It transmits data and works for basically getting logs and telemetry from your rocket, but nowhere near enough data for video. So talking about sort of the XB, the range the XB has is about 15 kilometers, which works for most, IREC competition rockets because that's well within their range. It doesn't use too much power, it's relatively efficient, and it has plenty of data for telemetry, but not nearly enough data by a factor of 10 for live video transmission. So you can sort of see, we have sort of a comparison of Space Shot and IREC, sort of saying that the XB would be totally suitable for IREC telemetry. It wouldn't be suitable for video under any conditions really, but it also wouldn't be suitable for Space Shot because it just doesn't have the range for sort of the more advanced rocket projects like that. So we designed our own radio. So our radio is based on sort of a heritage of previous radio technology developed at Stanford. So this is the ARIA radio. It's named after another student, Aria, who sort of developed it. He developed it for a balloon platform, so balloons that flew several hundred kilometers downrange. It was designed to communicate with them from the ground. So it was actually relatively effective. It also included a lot of other hardware. So it also includes the APRS, automatic packet recording system, so that sort of uses ham radio networks to communicate location. It had a lot of stuff that wouldn't really be applicable to rockets, sort of low data rate applications that are better for balloons that are in the air for an hour or a day, as opposed to a rocket which is in the air for a few minutes. So we had some improvements to make on that radio. So this is a picture of me testing this radio in a carbon fiber airframe, just to sort of quantify how that affected signal losses in our workspace. So the ARIA radio has significant improvements. It bumps the range to 150 kilometers, which is really impressive for a student-built radio of the first generation radio. It also decreases power by a factor of 3. This is really, really great, especially for a balloon platform, which is what it was designed for. The data rate is not that great, though, unfortunately. It's not really fast enough for an event like a rocket launch, and it's not really fast enough at all for video. So it's not really applicable to IREC or Space Shot, but it would be applicable to a high-altitude balloon. So we developed our own sort of radio solution, which Sharon will.
Hi everyone, I'm Sharon again. So to overcome those problems that the ARIA radio had, we built an SRADio or SRADio as an iteration on the ARIA radio. And our goals with this were to improve on the ARIA radio range by increasing the output power while holding the input power constant. We also wanted to just reduce the amount of power that we had to give the radio in the first place by removing extra hardware like that automatic packet reporting system. And we wanted to qualify this radio for use on our rocket, so we wanted it to pass shock and vibe. And then we wanted to integrate it into our rocket telemetry system. So we followed a timeline to make sure that we were ready for IREC in time. In October, we did scoping out of different choices, which meant we decided between the XP, the ARIA radio, and SRADio. During the design and simulation process, we read lots of app notes for different transceiver chips. We wrote code to simulate different combinations of passive components at our desired frequency of transmission, and we used a circuit design software called Altium to build our circuit. During the hardware and prototyping phase, we assembled PCBs we built and ran a revision 1 of the software. And then during the flight testing months, we built more PCBs, we tweaked certain component values to maximize output, and we uploaded some software updates. So the theory, as Tim mentioned, our goals in building SRADio were to reduce the noise, increase the output power we receive for a given input power, and increase the maximum data rate for a given range. So during that design and simulation phase that you just saw, we started with the XP as a working model of something that works for rockets, and looked at how changing certain parameters of the XP would affect noise generation, output power, and data rate. So basically we tweaked certain parameters, compared it to the XP, and saw ways that we could improve from the XP. So a couple important things that you need to know if you're not familiar to understand these next slides are power and gain. So power dissipated across the terminal is related to the current and voltage, so the current through a terminal and the voltage across a terminal. And then for gain, it's a measurement of the ratio between two voltages. So basically we use gain in these next slides to compare the voltage, sum-link voltage on our SRADio to that same voltage or that same measurement on the XP. And so here you can see the equation for gain in decibels. All right, so there are a couple governing equations that we use to try to maximize the power output in SRADio. And the first is the Friis transmission equation that determines the power received under ideal circumstances. As you can see, the power of the radio wave hitting the receiver depends on the power of the wave the transmitter transmits, the antenna gains, the wavelength, and the link distance. So the wavelength was basically already determined for us by the amateur radio band. We chose 433 megahertz because it fit in this EAGT band, and that's what our members are certified as at SSI. So if we plug that wavelength back into the Friis transmission equation, we get, you can see that going from the XP, which transmitted at a 33 centimeter wavelength, we bumped it up to a 70 centimeter wavelength, which gave us a 6 decibel gain in terms of power output compared to the XP. We did want to reduce the power, the input power that we gave to this radio compared to the XP, so we dropped it from 250 milliwatts to 100 milliwatts. And this results in a 4 dB loss in power received. Oh, and then we also wanted to increase the link distance for space shots. So going from 10 kilometers, which is what the XP transmits at, to 100 kilometers, that results in a 20 decibel loss at the power received compared to the XP. So the other thing that you want to consider when designing radio hardware is the bit rate, which determines the data rate. And as Tim mentioned, we wanted to increase the data rate from the ARIA radio. So this is the Shannon-Hartley channel equation, which governs the ideal bit rate that you can get out of a radio. All right, so as you saw on the previous slide, the signal to noise ratio is critical in this bit rate. So you want to make the bit rate you want to make the signal to noise ratio as high as possible so that you get as high of a data rate as possible. And so at 100 kilometers, we were getting Okay, so at 100 kilometers, we were getting 18 decibels of power loss compared to the XP. So we went with the SI Labs transceiver chip, and this is important because it determines the signal to noise ratio. That ratio is very dependent on the transceiver chip that you use. And using that transceiver chip, we decreased sensitivity by 10 decibels, but since it's in the denominator, that makes your signal to noise ratio go up. But we were still at 8 dB loss compared to the XP. So we wanted to improve this and improve our data rate by tuning the transceiver chip, which got us another 8 dB loss in noise, meaning that our signal to noise ratio went up. So we ended up with, at 100 kilometers, a net dB gain of 10 decibels compared to the XP. And at 500 bits per second, because we probably want to send, you can sometimes send that little data, you decrease the noise even more. All right, so that was all the theory that went into building SRADio, but then we actually had to build physical circuit and circuit board. So the circuit design, we started with the circuit design by following the app note circuits, and then we used an iterative solver to choose resistor, capacitor, and inductor values that the app note circuit lets you choose. And in comparison to the RIO radio, a big improvement that we made was we bought near lossless inductors and capacitors so that the components were near ideal and you didn't lose much in terms of non-ideal resistances in the capacitors and inductors. All right, so these are pretty important concepts to understand our next few slides. So SRADio uses frequency-dependent passive components, which means that these components have a reactance. And reactance fits into the idea of impedance, which is just the sum of resistance and reactance. And you can think of impedance as the inertia against the motion of electrons. So the two governing equations for inductors and capacitors are up on the board, and you can just see that the capacitor's reactance depends clearly on frequency, as does the inductor's reactance. All right, so the circuit design of SRADio, it really all boils down to this Class E power amplifier. And as I said before, the power through a terminal is equal to V times I. And the cool thing about this Class E power amplifier, you can see, is that voltage and current one of them is 0 the entire time. So that means that your power is 0 the entire time. Your power dissipated across the chip, which is really, really, really important, because that means that ideally you don't lose any power dissipated across your transceiver chip. So that's why you want to use a Class E power amplifier, and that is a big improvement from other radio models that we've seen. All right, so to build that Class E power amplifier, you have to do this matching network and resonant tank network. So as you can see on the board up here, the L0 and C0 make the Class E amplifier. Those are the two passive components that you need to make it so that you never dissipate any power across your chip. So those are the magic components. Now the tricky thing about this picture is that L0 in this picture is really Lx, which is a sum of the tank inductor and the matching inductor, but they just put them together on the picture because they're in series. So the tank inductor, the resonant tank inductor, goes into making that Class E power amplifier, but the matching inductor does something completely different. So we talked about what makes a Class E power amplifier, but what you also have to do is make sure that you provide a load impedance that is the complex conjugate of the output impedance of the power amplifier. So you want to match your antenna impedance essentially you want to match your antenna impedance with the impedance of your circuit. Because ideally, if that happens, you don't lose any power across your transmission circuit. Okay. So as you can see on this board, the things that are used in the matching circuit, which again is super, super critical to get that 50 ohms of matching impedance. We use LX, LM1, CM2, and or CM1 through 2 and LM1 through 3 to match the impedance of the antenna at the 433 megahertz rate. And this is why it's so critical that those components are frequency dependent, because at 433 megahertz, their reactance will be different than at a different frequency. All right, so to pick those critical values, those inductor and capacitor values that I just talked about on the previous slide, we wrote this iterative script that basically starts out by calculating the receiving balance values and then feeds those into a function that calculates the transmission resonant tank value, which is that Class E power amplifier, and then goes into designing that harmonic filter. And then you do a couple things. You solve for valid impedance matches, and then you select what kind of filter you want. In our case, we wanted a low-pass filter because we want to cut out frequencies that are above 433 megahertz. And then you simulate to calculate the ideal power loss, and then you iterate on that to try to minimize your power loss as much as possible. And so the harmonic design filter tool has a couple of tweakable parameters. You can change gain, cutoff frequency, the number of parts even that you use, the number of inductors and capacitors, and how sharp you want your filter to be. And so that leads to a bunch of different choices, but not all of the choices that our sort of simulation script spat out were good matches or led to good output powers. And so we wound up picking a fifth order Chebyshev filter. You saw that filter on the other page, yes, which offers a very sharp cutoff in terms of filters that it receives. So we really only get 433 megahertz, which is exactly what we want, and gives us a very narrow bandwidth. All right, so you can see some graphs generated by our filtering or our matching script. So the key things on here is this is plotting the power output in dBMs, which is decibel milliwatts, against frequency. And you can see that at 433 megahertz, there's this massive drop in terms of power that is transmitted through the receiver circuit. And you want to minimize power transmitted through the receiver circuit because that's power lost. And so it's really, really great here that at the inductor and capacitor values that we chose, we get a sharp drop in power lost. And then you can also see that we get our expected power output of about 20 dBMs at our transmission frequency of 433 megahertz. And again, this parameter low S11 indicates low loss transmission of power into the antenna. All right, so these are, those graphs that I just showed you were graphs of transmission power outputs with lossless components, so completely idealized components. But that's not how inductors and capacitors work in real life. When you transmit a certain frequency through them, they have some amount of resistance. And so the lighter blue line above shows the actual, the darker blue line shows the actual power output, and the lighter blue line above shows the ideal power output. So some pretty important things from this graph is that you still get a pretty low power loss when you have, or really low power loss at the desired frequency when you have non-ideal components. So even with the losses of the resistors, the sort of resistors that come along inherently with inductors and capacitors, you still get this nice sharp drop of power loss at the transmission frequency. And as you can see, there's really only less than a decibel of deviation between lossless components and components with some non-ideal loss. All right, so this was what our script said would happen when we picked these components, but then we actually had to build the radio in an actual circuit. So we designed the circuit in Altium, which is the circuit design software, and sent it to manufacturing at a local PCB manufacturer. PCBs are just printed circuit boards, for those of you who don't know. And then we assembled the PCBs, which means we placed the components on the PCBs, and brought them up and did lots of testing. So I'll show you those processes in more detail now. All right, so this is that circuit design software that I was talking about, Altium. This is the schematic, and you can see those that circuit that I showed you before, but now in the circuit design software. And then this is the hardware implementation. So what you saw was the schematics, a sort of circuit drawing, and this is what the actual board looked like. You do this thing called layout where you sort of draw the traces on the PCB, that's what those blue lines are. And then we sent it to a manufacturer. And then we got it back and assembled it, which meant we placed the components on by hand, soldered them down, and this is what a finished SRADio looks like. Now, a key thing is once you have this hardware, how do you get it to send the bits that you want across the air? Because it's just like a bunch of inductors and capacitors. And you do that with this SRADio software stack that one of our SSI engineers wrote. Basically, you take this SRADio software stack, takes in some serial data, parses it, and then does some error correction on that because you get lots of errors transmitting over air over long distances, puts that into binary data, and then SPI commands send that to the transceiver, that SI4463IC that I showed you earlier. The other thing that the parser does is it gets the configuration. So not only does it get the parsed message itself, but it gets the configuration, which means it gets the frequency, the modulation index, all that information, and also sends that to the transceiver. So the transceiver then has the information it needs to how it's going to transmit the message and the message itself. All right, so we tested this hardware that we built across Skyline, which is about 10 kilometer distance from Stanford, and it satisfied our needs for IREC and for space shot. So now Tim's going to tell you about the system design.
Yeah, okay, let's go through this. I think we're running out of time. Let's talk about system design. So we have some physical constraints on the actual installation of the radio into the rocket control system. So first of all, the avionics bay is only 12 inches long. That's a limitation. There's severe shock and vibe during launch and landing if it comes down hard. The rocket can sit on the pad for 4+ hours, as I'm sure we're all going to figure out tomorrow. And recovery can take a long time if you don't know where your rocket went exactly. So the goals of this telemetry system is to be able to put live position tracking, have a wireless altimeter and payload arming so we can remotely turn the systems on from a ground station, which means it's safer for the people setting up the rocket because nothing's on until the minute you turn it on wirelessly, and then have battery level monitoring so we know batteries aren't dying, and then failure detection. If there's a failure in the air or something goes wrong, we can know what happened only based on ground data without having to recover the rocket if it's a total loss. And then emergency recovery deployment. If the rocket becomes ballistic or it behaves unexpectedly, we can sort of deploy recovery and bring it down safely without endangering people. So the antenna design, that comes back to that 12-inch limitation for 70 centimeter wavelength, which is an increase from the XB's sort of 900 megahertz frequency, means it's 14-inch long antenna. In a perfect world, but that's not going to fit in a 12-inch avionics bay, so we looked at some different antenna options. The first is a slot antenna, so you can sort of see over here, the idea is you have a carbon fiber airframe body. If you cut the right size and shape slot and model it correctly in simulated software, you can use that slot in the conductive carbon fiber mesh as an antenna. So that's kind of, it's a bit out there of an idea, but it was definitely something we considered because it would solve a lot of our problems. So that is the antenna in rocket as opposed to antenna as a rocket. If your antenna is in a carbon fiber body, you have to have sort of some sort of more difficult antenna systems. So basically, the idea is with all these antennas is you sort of tune the length of the antennas to match the impedance of your output transmitter. So we set up all the impedance matching in that chip on the circuit board, and now we have to make sure the antenna properly matches that. We have basically a 50 ohm impedance match that we're trying to get to maximize power. So now shock and vibe tolerance is another thing. This has to survive a launch and landing. So first is high reliability pins. So we developed this sort of pin stacking system that has a lot of structural strength and rigidity and isn't going to sort of give way during launch. And then we tested the entire avionics bay on a sort of industrial shock and vibe table. So you can see over there, that's the avionics bay mounted, sort of clamped down and tested. So now we can talk about sort of, as a part of the avionics in general. So this is the radio that we developed, sort of this area, and then from the previous year we have the Skybass as a student research and developed altimeter system, so it has code that we write and can change, and then it's feeding the main telemetry sources, so GPS, inertial measurement, position orientation, and barometer into the SRADio data for downlink over the telemetry stream, and then it also receives telemetry about the battery systems, which aren't shown here, and then the Raven and Stratologger COTS altimeters are also fed into the radio for downlink. So we're basically monitoring all the systems through this wireless communication. It's very useful when you're doing the launch itself. So now, telemetry, this is sort of just a visual demonstration. This is a picture of the radio mounted to the bay. So we have these high-strength pins, and it's mounted here. This is the antenna coming out that way. We ended up going with an antenna, a commercial antenna, that sort of satisfied our needs because we ended up not doing a carbon fiber mesh body. It's fiberglass, so we didn't need to worry about that slot antenna anymore. And then that communicates with two things. First is the ground station, so we have a rugged high-temperature computer to survive out here in the desert, and it's sort of a 433 megahertz dipole that we can use to receive signals from these antennas and then sort of log the data. It's hard to see here, but this is Google Earth. So as the GPS data is coming down, the altitude and GPS coordinates are fed directly into Google Earth. You can watch the rocket rise as it launches, and you can see the full flight in real time. And then also it's used if you're needing to recover the rocket. This is a directional Yagi antenna connected to a handheld radio, and you can hear sort of the packets from this radio, and allows you to find the rocket if you lose it. So an example of telemetry that's happened. So this was our most recent launch. The rocket went up, and unfortunately at Mach dip, one of the COTS altimeters, the Raven, had an early deployment event. So it deployed when the rocket broke Mach, causing basically a complete loss of most of the rocket, because at Mach speed, separation is pretty violent. But we did get telemetry data, which told us what went wrong. So you can sort of see here, this is the packets of telemetry data that are coming down. So you can sort of see the packet numbers are increasing here, and then after this point they stop increasing. This is because we stopped getting signal. So data was no longer being fed in. And right before we stopped getting signal, the voltage, the other voltage value here, the voltage sense 2, this is the second chain of batteries in our redundant altimeter system, drops from 7.68 volts to 7.33 volts, and then back up to 7.6 volts. So what's going on here is the Raven altimeter is firing a charge, and that current draw is causing a drop of the battery voltage, and if you graph this, it's pretty clear to see that the voltage level remains constant and then drops right before we lose signal. And that told us, because that drop happened on voltage sense 2 and not voltage sense 1, which is powering the SRADio, we knew exactly which COTS altimeter had caused the error. We also knew that it wasn't our altimeter because we sort of have a lot of debug data coming through here that tells us that the altimeter had not fired. So sort of just an example of really useful ways you can sort of make use of a custom telemetry system to track the rocket through its entire flight. Yeah, okay, I'll just, iteration, we're making some new radios is the bottom line here. We're working on the next version, SRADio Rev 2, which is going to have increased range and also increased data rate and possibly less power. So we have a lot of acknowledgements to Aria, Joanne, Chloe, and Sky, and we have many references, lots of papers and things. If you guys have questions, we have a few minutes, I think.
That's it.
Yeah.
You did some fencing around the antenna.
Yeah. So the fencing is this is this is a 4-layer PCB. So the fencing is you're creating like a cradle around the feed line. So if you think about like a coaxial cable, there's a center core of copper, and then around it is like a metal sheath, like with some amount of like spacing in between. Which you're trying to aim for something like that here. You can't have copper over the top of the feed line in this case because the feed line is on the top of the PCB, so it's here. So if you sort of see the feed line here is on the top of the PCB, so there's no metal over the top, but you can get sort of a cradle around the bottom of that feed line, and all of that kit should be as grounded as possible. So by sort of including all those vias, which are just sort of connections through to the lower layer, you're sort of creating like a wall of metal, or in effect like a part of a Faraday cage, forming a cradle around that feed line, which reduces losses and makes it more like an optimal feed line. Yes.
Did you match the distance of these and the diameter of the vias to the actual frequency?
I didn't lay out the vias, so I don't know.
Can you repeat that?
Did we match the via size? Is it any particular size?
Oh, no.
Okay, I don't know. I don't think these are matched at any particular size. It's possible that you could optimize by doing that, but
one of the smallest that Altium let us do.
yeah.
And did you match it afterwards, or did you just match the? Do you have a circuit where you can match afterwards after you assemble and measure it, or is the line actually impedance controlled?
You can match afterwards in Altium. It runs once you put all your values down, it runs the expected impedance of the different trace lines in Altium.
What do you mean by tuning your chip?
Yeah, okay, so I can talk about that in particular. Some of that is sort of in the weeds in terms of software, but one of the main things we're doing is, so on this chip, this very bottom chip down here is a temperature-controlled crystal oscillator. So it's a crystal oscillator, a quartz crystal, that actually includes a heater built in. So internally it gets to a certain temperature where it's known that the chip is a very particular frequency, so it's extremely accurate, one of the most accurate sort of precision, like frequency generating devices. So the idea is, because we know that both sides of the radio connection have this very precise frequency standard that they can sort of tune themselves to in terms of the transmission frequency, we can reduce the bandwidth that the receiving circuit is tuning for. So if you don't know exactly what the transmitter is transmitting, because it may be slightly off, you have to scan a relatively wide bandwidth and say, you have to integrate your sort of receive function across like a wider bandwidth, because you don't know exactly where the receive will be. But if you know very precisely that like within like 20 kilohertz, it's going to be a very specific place, then you can say, you can reduce that bandwidth, which means you're integrating over less error. So you're reducing sort of the noise component in the signal to noise ratio by decreasing the amount of noise you're sort of collecting.
How do you do tuning?
So this chip has a ton of configuration options. It's got like thousands of registers that you can program through the configurations. So basically, by just including this chip and then sort of trying smaller and smaller bandwidths to get the signal to noise ratio up until it starts going down, you can sort of say like this is the optimal sort of tuning like that. So a lot of it is just sort of software and then repeated trial and error in a controlled environment, sort of controlling for loss.
Well, and appropriately using the crystal oscillator. It wasn't appropriately used on our first ARIA radio, so very specifically following the app note lets you get a lot better performance out of the crystal oscillator and the SI Labs chip.
In other words, read the instructions, right?
Yes.
Thank you.
Any other questions? No? We have some appendices. They're not going to be very interesting. This is all the data we're sending. So you can sort of see a pie chart, latitude, longitude, the packet number, which represents time, the altitude, and the COTS altitude, and then battery voltages. We developed sort of an algorithm for compression here. Oh, sorry.
What's the longest range accomplished?
Okay, so the longest range. So with the ARIA radio, so the older version, there was a balloon test that reached 200 kilometers. So we have tested in a real world test without any sort of faking it, 200 kilometers through the atmosphere. So but it could theoretically go farther than that, but yeah.
And across Skyline, we simulated longer
Yeah.
with using attenuators. We stood 10 kilometers apart, and then we added attenuators to our antenna, and I believe we got up to 400 kilometers.
Yeah, 400. So by adding attenuators to the output, you can sort of simulate a farther distance because you know how that distance will affect signal. So you can simulate we simulated up to 400 kilometers, and we're able to still receive data.
But I think 5 bits per 500 bits per second. Yeah.
Yeah. So by decreasing to 500 bits per second, you sort of increase your range a little bit. You sort of are getting a little bit more out of the signal by sending the packets slower to make sure they're better received.
Did you manage to transmit video?
We have not yet transmitted video. That is a project that's going to be in the works under the next